Okay, good morning. So I just write there the value that we found for the limit temperature in a Doppler model. It is just a reminder to have it just there. And I will start the next part, the subdoppler cooling, with some historical consideration. So if you take this limit temperature and you compute the value for sodium, then you find that the minimum temperature is equal to 240 micro-K. And if you go to see the first publication by Chu et al. In 85, you find that they have indeed measured 240 microkelvin. But if you look carefully, you see that the error bar are rather strange, because it is plus 20 and minus 80. So probably this means that they have measured a temperature that was lower than the theoretical minimum temperature, but they didn't dare to publish it. Okay, so how was the experiment done at that time? The only method to measure the temperature is the time of flight measurement. So, okay, well, some wiggles are missing, but it doesn't matter. And do you know it? You practice it, or it is outdated? Still? Everybody, or? Not so sure. Okay, so I will spend a few. So the idea is just to trap atoms. So obviously you have to be able to trap atoms. And then you switch everything off. And you have, at that point, you have gravity and your atom fall down. So if they were at zero temperature, they would just fall down as a solid cloud. But in fact, they have some initial velocity in any direction. And you measure, in fact, with a light sheet, just as a given distance below the MOT, then you measure the time the atoms are needed. They need to go and cross this sheet of light. And what you measure is just, you measure the absorption of the resonant light that is here. So the idea is very simple. So if this is the H, and if the cloud was just at zero temperature, then you just have to write 1/2 GT naught 0 equal to H, and that's it. You have the time it needs to reach the minimum. But if you just now have an atom which starts from a position Z0 in the cloud with a velocity V0, a vertical velocity, the horizontal one doesn't give any importance, and then it will arrive at, so you just see the time it takes to reach the sheet of light, and you introduce this TH, and it's just in the first approximation a delta t, and then you compute delta t, and you find that it is V0 divided by G plus Z0 divided by G T0. And at that point, what you measure is the spread in the arrival time, because you just look at the absorption with the scope, and you see something like that, usually a Gaussian, or you think it is a Gaussian, you hope it is a Gaussian, and you measure the width, so either at 1 over a or 1/2 or any value you want, and you just say that you have this time for a given V0 and Z0, and at that point you average this arrival time, so my delta t, and if everything is Gaussian, then you have a Gaussian at the end, and the Gaussian is just, so you have a cloud with, so it is Gaussian, and a velocity distribution which is delta v, and then you can easily show that you have both contributions. And if you can neglect the size of the cloud, it is just you have the delta Vz equal to G delta T. But obviously you have the systematics, which is the spread in the cloud. Okay, so if you go now to cesium, the Doppler temperature is on the order of microkelvin. And so the delta V, the corresponding delta V is a few centimeters per second. And if you want to, so if this is not too large compared to the height of the, you just choose 10 centimeters height, and then you have a T0, which is milliseconds. Okay, and this leads to the experimental results better than the first ones. And so you have in the 1988, you have a result by Lett et al. In the group of Bill Phillips. And they have measured temperature down to 50 microkelvin for large detuning, and they observe that the temperature goes down with the detuning, which is not what you expect from this formula. If you are at large detuning, you expect to have a temperature that grows with the temperature. 2 years later, at the ENS, they measure that the temperature grows linearly with the intensity. And in the Doppler model, you have the diffusion coefficient, which is proportional to the intensity, but the friction coefficient is proportional to the intensity. And so the ratio of the two, which is the limit temperature, do not depend on the intensity. And they also have what they call a universal. You must be careful when you use words like that, because it was a bit, so now it looks a bit strange to call it, which is that the temperature is proportional to the intensity divided by the detuning. Okay, so what is wrong in the Doppler model? Because obviously the experimental results show that something is wrong. And what is wrong is that the Doppler model rely on a 3-level atom. And if you look at the alkali that was used at that time and still now, in fact, you have many level atoms. And if you look just for cesium, because I know it pretty well, you have F equal 4 to F prime equal 5 transition, which means that here in the ground state you have 9 sublevels, and here you have 11 sublevels, so a lot of levels. Too many. Okay. So at that point came into play the sub-Doppler mechanism, and I will talk mainly of the Sisyphus cooling. There is another scheme which leads also to lower temperature, but maybe I will say a few words about it in a moment. And so the system under consideration is just, so we will take the simplest complicated transition, which is 1/2 3/2 transition, which means that you have 4 excited levels and 2 ground levels. So minus 1/2 plus 1/2. So minus 3/2 minus 1/2 plus 1/2 plus 3/2. And so this kind of atom is sensitive to the polarization of light, and probably you are already familiar with that. You have the Clebsch-Gordon coefficients. And in this case, these Clebsch-Gordon coefficients are just 1 divided by square root of 3. Here you have of 2/3, and here obviously you have just 1. You know the Clebsch-Gordon coefficients? Yes? Yes. Okay. And so this is the atom, and the light field is just a 1D configuration with 2 opposite beams, one propagating in the plus Z direction and the other one in the minus Z direction. And you have this one which is X polarized, and this one is Y polarized. So it means that you will write E1 as, so the amplitude EL divided by 2, and you will have exponential minus I omega LT plus I kz unitary vector along X plus CC. And the second will be the same EL divided by 2, and you have just I, the same frequency, but and the other polarization, and plus CC. So you just sum them up and do a little exercises. And if I just introduced the sigma plus and sigma minus light, I will have so exponential minus I omega LT times cos kz and plus I sin kz, and here I have up plus CC. And so there are the sigma plus and sigma minus. So this one, so it depends. You can have different definition for the sigma plus and sigma minus modulo some factor or some I somewhere, but so you have the sum. Sorry, this is sigma minus. And so this means that the resulting field so if I just plot along the z direction, in 0 I have a sigma plus polarized light. If I go to lambda divided by 4, at that point I have a sigma minus light, and then again at lambda divided by 2 I have a sigma plus light. And so in between I have here a linear polarization, let's say at 45 degrees respect of x and y. And here again I have a linear at, let's say, minus 45 degrees respect to the. And because of the Clebsch-Gordon coefficients, you have a different coupling for the two sublevels to the different polarization. And so the coupling to the light depends on the position. So a few words about the dressed atom. So we have already seen it in the lecture of Jean-Michel. So the basic idea is just to have your bare atom, and you add the field, which has a ladder of levels. But the difference between Jean-Michel's talk and my feeling is that I am interested in intense laser field. So what occurs for the n equals 0 level is somewhere near the center of the Earth or even below. And so it doesn't matter a lot. I am just interested in the level n minus 1, n plus 1, etc., with n on the order of n bar, which is large respect to 1, which means that the populated state of the laser field are just somewhere between minus square root of n squared and a maximum value which is typically, so it is not obviously strictly speaking limited in this range, but the main idea is that this number n is almost a constant. In fact, you have seen in Misha's lecture almost the same treatment when you consider in the Bose-Einstein condensate that the operator A0, creation or annihilation in the ground state, is so large that you can replace the operator by a number. And here I will do the same. Each time I will see A or A dagger, I will say that they are square root of the mean value. So it changed things in the sense that instead of having couplings that depends on the level, you have all the same couplings. So obviously my drawing waste the place I expect to use. So I have, if you sum just these two, you have J and n minus 1, and somewhere here you have E n minus 1, and you have J n, and obviously here you would have E n minus 2, and you have the same pair. So I make the drawing for delta negative, because for me it's the situation where I am interested in. And so to recall, so this distance is omega 0, and this one is omega L. So I think, if I remember correctly, in the original model, in the original description of the dressed atom by Cohen-Tanuji, he have the reverse detuning. So his detuning was omega 0 minus omega L, while my detuning is omega L minus omega 0.
I have the Cohen version.
Yes, exactly. There is a sign somewhere. This is the reason why because if now, so I don't remake the derivation. You have here coupled levels, and here coupled levels, and all you have to do is in the resonant rotating wave approximation, you just take into account only the resonant part of the coupling, and you end up with the something, the energy, the eigenvalues are En, so the mean energy for the multiplicity, plus or minus h bar divided by 2, something which is the square of the detuning plus the square of the coupling. Sometimes this is called the generalized Rabi frequency. And if you plot now the energy as a function of the detuning, you will have the bare levels that are going like that. And in my notation, Gn is here, while in the slides of Jean-Michel it was here, and this was E n minus 1. And the coupled levels are hyperbola that are just somewhere there. So this is just the Rabi frequency. And so that's it. Yes, just one remark. You remember, probably, it puzzled you. I have written somewhere a long time ago that you need to have the condition omega 1 much smaller than omega 0 to be allowed to apply the rotating wave approximation. And so what is interesting is to try to understand that in the dressed atom approach. So usually this is the more or less, this is in the bare, so this is the bare representation, bare nude atom, bare atom plus field, obviously. So this, you have just the detuning, which is much smaller than omega 0. If now you consider a splitting with a Rabi frequency which is on the order of omega 0, it means that this level jumps here, this level jumps there, and this one jumps here, and this one jumps up there, and a guy from there goes down here. And if you look what is going on in this kind of submultiplicity, then you see that these two levels are precisely coupled by the non-resonant part of the coupling Hamiltonian. And so it means that if you have omega 1 which becomes on the order of omega naught, you have a mess because you have levels that were simple to treat that mix up with some others, and in fact you can do nothing because everything is coupled. And so fortunately in the optical domain it is never so this condition is always fulfilled and you never have such a mess. Okay, got it? It was just a remark en passant, as we say. So at that point, what interests us is just the shift of the level, which was introduced as S in Jean-Michel's talk, but I will avoid to use S because S is the saturation parameter for me. And in fact, so it is, so this is the energy, and you just have to subtract the energy of the multiplicity. So at that point, it is h bar divided by 2. So I can drop the h bar and delta squared plus omega 1 squared minus delta. So probably as delta is negative, if you want a positive quantity, you have to have a plus here. And when you are in the condition where the low saturation regime, so you have omega 1 which is smaller than, sorry, 1/2 of delta. When omega 1 is smaller, then you end up, you can make the expansion of that, and you find that the result is 1/4 of omega 1 squared divided by delta. this is the light shift. And so in the limit. Okay. This being said, we can go back to now, in our particular case, to the light shift of the ground state states, because we have two ground state. And in fact, if you look at your system, you have sigma plus and sigma minus light. And so you have one system which turns out to be here. And you have a second V system, which is very nicely independent on the first one. And at that point, you just have to, you can write, so this level will be shifted with a U plus, which depend on the position. This one will be shifted with a U minus, which depend on the position. And the two contributions just sum up, and so you just have to write something which is U plus of Z, which is obviously you have H divided by 4 delta, the same that is here. You have an omega 1 squared. And so this is the plus, so it takes the sigma plus light with the Clebsch-Gordon coefficient of 1. So you have just simply the sigma plus light is cosine Z. So it is cosine squared Z. And you have to add the contribution for the sigma minus light. And this one is just 1/3 of sine square. The third be coming from the Clebsch-Gordon coefficient. And the U minus of Z, you just have the same thing, but the sine and the cosine just switch. So you can also work it out saying that this is not so nice to have a sign here. And so instead of that, you say that 1 is equal to 1/3 plus 2/3, which is always true. And when you have 1/3 of cosine plus 1/3 of sine squared, it is just 1/3. And so it turns out to be 1/3 plus 2/3 of cosine squared kz. And obviously here you have the same, which is 1/3 plus 2/3 of sine squared kz. Just note that here, this omega 1 is not the Rabi frequency associated with one beam. You have here a square root of 2. It is the intensity of the sigma plus light at the maximum. So it is 2 times the intensity, so it is related to twice the intensity of a beam. So just one remark, if you go to higher transition, with more levels, it becomes rapidly a mess. So this is just a remark. For instance, if you're just looking for a j equal 1 to a j prime equal 2 transition, then in fact you have a nice V again here, but the other one becomes a W here, and it is rather, so it is more complicated to treat it. So there is a simple way. So this guy is just boring because the sum of the two is just constant. So the energy of this guy is just remain there. So this is m equals 0. If I now just think of cutting this level in two pieces and just forget it for a second that it is only one level that is here, then you have a V system here and there, and so you have the same result. You expect to have a sinusoidal modulation of the intensities. And obviously, this level is just 1. And so where does the fact that this level is just 1 have to be taken into account? It is just here, where you have crossings. If you have crossings, then any coupling will lift this crossing, and you will end up with what is called the adiabatic levels, which is roughly something like that. So obviously I do not tell you what is the splitting and so on. It depends. So you have to make the calculation, the full calculation. But just to give you a picture of what happens is just that. You have, if you just forget that here in the middle you have the same level, then you have just sine and cosine modulation, and the coupling lift the avoided, so the crossing becomes an avoided crossing in the center. Okay. So this was just a remark, so I can erase it. And now, this D, I arrive to the optical pumping. And the words optical pumping reminds you obviously of Kessler and what pointed out Jean-Michel on Tuesday is that in a footnote, I think, it was a footnote, he mentioned the effect lumino-frigorique, so which means that he has already the idea that optical pumping can be used to cool atoms. Okay, so what is the optical pumping? It's just in your atom, you have, when you are in an upper level, when your atom is sitting here, okay, very nice. This, it has only one thing to do, is to decay because of the selection rules. It can decay only here. If it is here, it can decay only here, and everything is fine. Obviously, what is nice for us is that when the atom is here, he has two channels to decay, and the same as here. And you have branching ratios, which are just given by the square value of the Clebsch-Gordon coefficients. So I am interested, so the E excited level plus 1/2 can go either to the G minus 1/2, either to the G plus 1/2, and this one is with 1/3 a probability, and this is a 2/3 probability. So when I am looking in a position where I have sigma plus light, so it was in 0 or in lambda divided by 2, then if the atom is in the ground state in the plus 1/2 level, the only thing it can do is to absorb sigma plus photon, because they are the only available, and it decay back here. So in the sigma plus light, this level is, let's say, stable, in the sense that the atom will leave it, but it turns back to the same level. On the other hand, if you start from the other ground state sublevel, then you are excited from here to there, and from there you have 2 times more probability to go down here than to turn back to the original state. So which means that you have a branching probability to go to the plus 1/2 level, and then you are blocked there. And vice versa, obviously, for sigma minus light. And what we will write is just rate for going from the minus 1/2 to the plus 1/2. And so this is just, you have the 2/3 of gamma. So this is the probability to go down. And you have the probability to be excited and the probability to be excited. So you are in the minus 1 level. So the probability to be excited is 1/3 of the usual. You have the coupling 1/3. So it is 1/3 of omega 1 squared divided by 2 divided by delta squared plus gamma squared divided by 4, and obviously the cosine kz. So this is the intensity of the sigma plus light. With the 1/3, it is the Clebsch-Gordon coefficient. So this is the population of the excited level plus 1/2 due to the presence of sigma plus light. And this is the excitation rate, so the probability to end up in the plus level. And you just have to write the same. And so this, you recognize this quantity. You know it? Yes? No? So I think it is 1/2 of S. So I'm not sure of the half, so you probably have to check gamma F kz. And what is nice is that at that point you have a correlation between the energy of the sublevels and on the optical pumping rate. And this correlation gives you an efficient optical pumping and light shift. And so this leads to an efficient cooling. So a way to see that is just to draw the two levels. So just make some Technicolor drawings. So the plus level is like that. The minus level goes like that. And you are just an atom that is here, but with a velocity like that. So here you just have to climb the hill. You climb the hill and, oh, I am in the -1/2 level, and here I have sigma plus light. So what happens is that at one point, somewhere here, I am excited to the upper level, which is far above, and I come back here. And again, I am at the bottom of a hill, so I have to climb. And at that point, I have a sigma minus light, and once again, I am excited, and I fall down here. So in this process, going up the hill, you have to transform your kinetic energy into potential energy. And with the optical pumping cycle, you just lose your potential energy. And so once again, you have to convert your kinetic energy into potential energy, and you lose it again. So each time you progress, you lose energy. At one point, you will just have to stay in one potential well because you have lost all your kinetic energy. So this is just hand-waving drawings. You can make, obviously, all the calculations you want. And even if you don't want, so if you stay in one level, so in fact I don't need the vectors, and I have only one dimension, so it is d over dz. So I have a force that a priori depends on the level I am. I am not the atom, but the atom sits in on one level, and so it has a force, and the total force is just the ponderated force with the population. And you just have to turn the crank. And for a moving atom, you have the population depends also on the velocity, and you just go on. And yes, I have forgot. Okay. So at the end of the day, you have a minus alpha v divided by 1 plus b squared divided by a capture velocity. So sometimes you can put that in the, but here you have alpha, that is 3 h bar k squared delta divided by gamma. I think I have to put here an absolute value. And you have the capture range, which is just what is called the gamma, what was called gamma prime or small gamma divided by 2, and in fact this is gamma prime. Is in fact the spontaneous emission. It is in fact the width of the lower level due to the coupling with the excited level. Okay. Yes. So alpha increases with the detuning, but at the same time, the capture range decreases with the detuning. So if we comparison with Doppler cooling, then in the Doppler cooling you can also define a capture range which is either delta divided by k or gamma divided by k. It depends. In fact, it is the larger of the two quantities. And so the cooling, no, I didn't write it. Okay, too bad. And the friction Doppler friction coefficient was just 2s h bar k squared delta gamma divided by delta squared plus gamma squared divided by 2 by 4, sorry. And so you just now you can compare both friction coefficient. So you just compute alpha d divided by alpha Sisyphus cooling, and you find out that it is something that is s gamma squared divided by delta squared plus gamma squared divided by 4. And as you assume that s is small because you are in the low saturation regime, you find out that the friction coefficient for the Doppler cooling is much smaller than the friction coefficient for the Sisyphus cooling. But on the other hand, if you compare the capture, so this is for the Doppler cooling with the same for the Sisyphus cooling, then you find that it is more or less 1 divided by s. So this one is much larger than unity. So if you just want to draw the force just as a function of the velocity of the atom, so the Doppler cooling, it was the difference between two Lorentzians, so it looks like a dispersion, but it is not a dispersion. And so this is the Doppler. And on top of that, you will have the Sisyphus cooling that has almost the same height, but which is much steeper in the center, but also much narrower on its application. Okay, so maybe I can, yes, I will erase that at that point. So the natural question at that point, so probably it is E, is the limit temperature. Okay, so you remember how we did it? So we can do it again, but I will not do it. So the principle is simple. You just introduced a coefficient, diffusion coefficient in momentum space, which is due to the effect of, and you just write down that you will have a Kb Sisyphus temperature, which is ds divided by alpha s. And so, okay, And so it turns out that at the end of the day, you end up with something which is u0 divided by 4, which is finally what I was drawing here. In fact, as is if your kinetic energy is sufficient to go above this crossing point, then you have a non-negligible probability to go there, and then to end up with an energy that is slightly lower than the crossing point. So it means that u0 being the total depth of the potential, it means that you are not allowed to have a kinetic energy has to be lower than u divided by 2, and just hand-waving arguments say that your kinetic energy is positive, is bounded by u0 divided by 2, so it mean value so just hand-waving arguments, but it works, so we are happy. Okay. So at that point, I will maybe have troubles with Hélène, because I am going to avoid any problem, I add some words: deep, dissipative, optical lattice.
You are allowed to do that.
Hmm?
You are allowed to do that.
Okay, thank you. I have added these two words because she will spoke of conservative optical lattices and shallow optical lattices. So not so deep. Okay, so the idea is that in this case, when you have u0, which is much larger than, say, the recall energy for the atoms.
I have a question regarding the unit temperature.
Yes?
What's the limiting factor of this temperature? Like if I decrease the amplitude of the intensity of my laser, I feel like I can go to 0.
Yes, yes. This has been studied extensively, and it is known as the Decocharge. And in fact, if you plot the temperature as a function of the potential, in fact, you have this linear behavior down to a value where you have something like that. And typically, we will say a few recall energies. In fact, as soon as if you reduce too much the saturation parameter, then this peak to peak becomes very, very narrow, and you always escape the range where the Sisyphus force is relevant. And so you have a limiting factor, which is the recall energy. And so if for each spontaneous photon you can, if you just sit here and if you consider then a single photon put you there, then you will not be sensitive to the Sisyphus force again. And so at one point the Sisyphus cooling mechanism breaks down. Okay, so as a matter of fact, U naught can be, so it is just 1 squared divided by delta. And you can imagine to have that quantity on the order of the line width, even a few of them. And so it means that you have the potential energy, which is on the order of 1,000 recoil energy. And this is a very nice situation, because at that point you say that everything will occur at the bottom of the well, and instead of considering a sinusoidal well, you just consider a parabola, and the parabola is a harmonic oscillator, and you will say that you have an oscillation frequency which is just the one of the which is twice U naught in recoil. And so in this harmonic potential you just have equidistant levels. And if you look at the rate of excitation, desexcitation, and the coupling between the levels, you have a kind of thermal equilibrium in the population of these vibrational levels. And a long, long time ago, I did some pump probe spectroscopy on this level. And so, in fact, you couple the atoms with the pumping laser with a frequency omega pump. No, yes. And you add a second laser at a different frequency omega probe. So, okay, pump and probe. And each time you have the difference, that if the difference is just equal to this omega oscillation, then you have stimulated Raman processes where you can absorb one pump photon and emit a probe photon. Obviously, you have also the reverse process where you absorb a probe photon and emit a pump photon. But the reverse process is weighted with the population which sits here, and not the population that sits there. And as soon as you have a cooling mechanism that maintains the population independently of the probing, then you will see an amplification of the probe when the frequency of the probe is smaller than the frequency of the pump. And on the other side, you will see an absorption. And so this is minus omega ask, this is 0, and this is omega probe minus omega pump. And so I did that in my youth, and we published it. And that's it. Okay. Do I switch to higher dimension, or do I say a few words? Yes, maybe I go to higher dimension. And then I will say also a few words in the last minutes of the second cooling mechanism, subdoppler. Okay. So up to now, we, so I don't know, higher dimension. So up to now, we have one beam like that and one beam like that, and we have a 1D situation. And the question is how I will do a 2D optical lattice or a 3D optical lattice, obviously also a 4D or 5D, but this is more difficult. And just for that, we consider that we have n plane waves that are interfering. And so the total field, just scalar, I don't need it to be a vector, is just, we just assume that they have all the same intensity. And we have then the sum for GA equal 1 to n of the wave, the plus A K J R. So this is just the plane waves. And so this is not so nice. And I prefer to write it in a different way, which is sum over j equal 1 to n minus 1 of exponential I kj minus the last one plus 1, because it is the last one. And I put A kn r here. Just a trick. Now, assume that you find a vector A such that exponential, so no, just kj minus kn times A is equal to 2 pi times an integer that depends on j, and this whatever j is. This is fantastic. It means that this vector leaves the field invariant just with a phase factor, but as usual the phase factor is of no consequences. So this A, if I find one, is an invariant translation of the lattice. And if you remember properly your solid state physics course, it means that these wave vectors, which I will call kappa j, are the basis of the so-called reciprocal lattice. And so this tells you also that if you are in 2D and if you don't want to have troubles, in 2D you are allowed to have only 2 vectors in the reciprocal lattice. And so it means that to make a 2D lattice, you just have to use 3 beams and not 4 if you do not want to have troubles. So then you can arrange them as you want. Obviously, the most symmetrical way to arrange 3 beams in a plane is just with 120 degrees between them, but probably nothing prevents you to put your 3 beams like that if you prefer. Okay, but use 3 beam in 2D if you do not want to have troubles. And obviously in 3D it is 4 beams and so on. But obviously I will not follow my precepts because it would not be so funny. And I will follow my spontaneous, deeply anchored Cartesian way of thinking. And for a 2D situation, my spontaneous tendency would be to put two beams like that to make a 1D optical potential and add two beams like that to have an orthogonal optical potential. But now I am considering the case where all the beams have the same polarization, and so they are all interfering. So it is two interfering standing waves. Standing waves. Okay. At that point, I have a problem in my definition of K because I have not, if I just take these two, so this is K4, this is K1, K2, and K3. I have the natural kappa 1 here, kappa 2 here, and the kappa 3 is just equal to kappa 1 plus kappa 2. Maybe you have a sign somewhere, but it's something like that. Okay, if now I have standing waves, so they have fixed phases in space, and I can consider just my first standing wave is the horizontal one. So this is the node. Then you have the second node with the opposite sign. And once again a node. And again the opposite node. So these are nodes, negative, negative, negative. And this is positive, positive. On the other direction, you have the same thing. So you have positive nodes and in between. So the spacing is the same, even if it is not obvious from my drawing. One second. Okay. So what happens if you are sitting in a positive node for one standing wave and a negative node for the other? Then you have here a 0, because the two amplitude cancels. So 0, 0, 0, 0, and obviously also 0, 0. So you have a lot of zeros. And if you look here, you have a big, huge maximum of intensity. And here also, you have a big, huge maximum in intensity. If they are interfering, which means in the case where the phase between the two standing waves is 0, then, so here you have positive. And so if you are considering a delta negative situation, then the atoms fall in the high intensity region. And so for the phase phi equals 0, where you have interference, then you will have an atom here, an atom there, an atom here, an atom there. So with a spacing here, which is lambda divided by 2, and this one, which is just halfway in between. On the other hand, if you consider the case where your phase is pi over 2, which means that the two fields just beat in quadrature, then they just sum up everywhere. You have no destructive interference here, and at that point, for the phi equal pi over 2, you have twice as much sites to trap the atoms. You have a square lattice, which is slightly puzzling, because just changing the phase between the two standing waves, you have the impression that you change completely the structure of your lattice. In fact, it is not true. You do not change it. Because here you see this square and you think, okay, this is the first Brillouin zone. But this is not true. The first Brillouin zone is not this one. In fact, the first Brillouin zone is this one. And it remains always this one. Simply, in this case, and in fact in every situation, you have a decorated first Brillouin zone, which means that in the first Brillouin zone, you do not have only one minimum of potential, but you have two of them. In the case where the phase is pi over 2, the two minima are fully equivalent, so they have the same depth. For any other value of the phi, you have one potential depth that is deeper than the other one. And the special case phi equals 0 just means that the second one vanishes. And so it is not a magic sudden change in the Bravais lattice. It is just the fact that you always have two minima in the first Brillouin zone. Just in this case, one minimum disappeared. Okay, yes, 10 minutes. Okay, this was almost everything about Sisyphus cooling, and there is another situation which, depending on the vocabulary, it is the corkscrew molasses, or sigma plus, sigma minus molasses. And in fact, it is the direct evolution of the Doppler cooling, where you have in one direction a sigma plus light, and in the other direction you have a sigma minus light. Yes, maybe one point I forgot is that we are just doing atomic physics, and not optics. And so the sigma plus and sigma minus light are defined with respect to a quantization axis that I have chosen at the beginning of my treatment, and not as for the optician, which stands in front of the laser, looking at the laser coming into his eyes and saying this is a sigma plus and this is a sigma minus. It's a very bad idea to have the laser coming into your eye, so avoid to use. So these are sigma plus and sigma minus polarization for AMO physicist, not for an optician. You know, there are some strange things for an optician. When a beam bounces on a mirror, its polarization changes. So the field rotates always on in the same direction with respect to the quantization axis. Okay, so this was just a parenthesis. So if you now look at the sum of a sigma plus and sigma minus beam with the same intensity, then you know that sigma plus plus sigma minus gives you a linear polarization. And so everywhere you have a linear total field, but simply it rotates in space, so it is rather difficult to draw it. But so, okay. You have a kind of spiral, and you have, when you go on, you have your. So I never know if it turns this way or this way, but it doesn't depend. It doesn't matter. So, if you consider an atom at rest, then the natural thing to do is not to choose the quantization axis as usual there, but you have an electric field which is linear. Then you choose the direction of this electric field as the quantization axis. I can do that because my atom is at rest. So I know where I am. My atom is there. I have the quantization axis. And I will consider the simplest transition where this kind of phenomena appears, which is the j equal 1 to j equal 2 transition. You know, it's the progression. We start with 2, 3, then 6, and then we are, I don't know. So the advantage to choose this, the field along the quantization axis, is that my field is just standing here. So once again, I can write the Clebsch-Gordon coefficients, and I'm not sure to be able to find them. 1 divided by 6. 1 divided by 2, sorry, this one, and 1, and so it means that here you have 3, 2, 1/3. Okay, so I do not remember. 1, 2, 3. Where I have it somewhere. No, too bad. I have to recompute them. Sorry. Alors, 1/6, 3/6, 6/6. Ici, ça sera. C'est un demi. Non. 2/3. 2/3, ce serait bien. Hein. Et ici un demi. Non? So the trick to find them is to just add 1, then you add 2, and then you have 6, and then you just have, here you have 1, so they become all divided by 6, and here you have 1 divided by 6 coming from here, 1 divided by 6 coming from there, and the sum should be 1. So it means that here you have 2/3 plus 1/3, which is 1. And here you have 1/2, and so this is 1/2. Okay. That's it. So, sorry for, I did not prepare that. And so it means that now, because of the light shift, this level goes down, and these two levels will go down, but slightly less, because this is 2/3 and this is 1/2. And now the next step is the optical pumping, and it is not so nice as the Sisyphus cooling because you have no stable states. Because as soon as you come up here, you can go down either there or there with 1/2 and 1/2 probability. The same here. And here also you have the 3 branching ratios. But if you just make the calculation with the same argument, just going up, and you calculate the probability to go from here to there, from here to there, from there to here, and so on, you end up with stationary population, with a population here which is larger than the 2 population here and here. So once again, it is due to the optical pumping. So contrarily to the Sisyphus cooling, you do not put all the atoms in one of the magnetic sublevel. You still have some everywhere, but you have more atoms in the more displaced level. So if you want to treat now a moving atom, the proper way to do that is to introduce the fictitious magnetic field that represent the motion, the change in quantization axis due to the motion of the atom. But there is a simple way to do that. Is just consider that you have your atom that sits here, and then suddenly you move it from here to there. So you don't want to know how you do that, but you did it, just thinking. And at that point, you have changed the quantization axis. You had these populations with this quantization axis, and now I jump slightly further, and my quantization axis has changed. So I have to make shares in that population, and one part goes here, one part goes there, and the same amount of this population goes back here, and the same amount of this population goes there. But the net effect is that you reduce the population of the 0 level, and you increase the plus or minus 1 population, because you just take the same part of a larger pie and you put it in between, and so you will have a larger pie. You see that? Yes, you have a question.
So in experimentally speaking, the
So in this case, I have no magnetic field. I do not have any magnetic field. I am looking just at a corkscrew molasses. It is not the magneto-optical trap.
Yeah, so, okay, but when you say that the electric field is linear with the quantization axis, experimentally speaking, what's defined the quantization axis?
Nothing. You choose it. As soon as you have no special constraint, so you do not have any magnetic field here, because it is a molasses and not a magneto-optical trap, you are not obliged to choose the quantization axis along the axis of the beam, which is the direction of the magnetic field. You can choose the quantization axis in any direction. And you choose it in the way that is more convenient for you. And if you choose the quantization axis here, then you have everywhere two fields, sigma plus, sigma minus, and you have to compute the result for this one and the result for these two, and it is a bit messy. I prefer to say that I choose my quantization axis along the electric field, so I have only a pi polarized electric field. And at that point, for the coupling between the atom and the field, I have no problems. This is my choice. And I am allowed to do that because my atom is at rest. In fact, it becomes what is simple for an atom at rest becomes complicated for a moving atom. So in this picture, I just give the fact that the atom can move with hand-waving arguments. But you see that as soon as you displace your atom, I don't want to know how you do it, you increase the population in the side levels, and you decrease the population in the center. And so it means that to reach again the steady state, which means you have to put again the population here, you have to reduce the energy. So I'm not sure I have convinced you, but you can make all the calculation. And if you want the detail, I think that they are in the paper Josabe 88. 89? Okay, so 89. Thank you. So it is the famous paper about the so-called new mechanisms, which explain all the subdoppler coolings. Okay, I am late. I stop.
Perhaps we can stop there. Is there any questions, or you can directly ask your Yeah, one more.
Yeah, suppose I do want to make 2D lattice with the 4 beam but not 3 beams. How can I play back? What's the technique to play back?
You have a very nice paper. What was his name? Emmerich, and in the group of Ted Hensch in 92, yes, probably, where they did it. In fact, so in Paris we observed the first pump flow spectroscopy in a 1D lattice, and we published it. And a few months after, the group of Ted Hensch published the 2D optical lattice. But in the meantime, we realized that it is better to do the 2D lattice with 3 beams instead of 4, and so we had a fight with Ench, but obviously we lose, but it doesn't matter. So you can do it. In fact, if you just have the same standing wave and you lock properly the phase, then it's okay. But it's hard work, anyhow. But you can do it.